Hello everyone. While drafting an email or a document in Google Docs, you guys must have noticed that the editor itself suggests the way to complete the sentence. Ever wondered how these applications predict what you want to write? Well, if you have ever wondered or ever felt curious about this phenomena, then you are at the right place. Today we are going to explore basic details about the machine learning algorithm that Google has implemented in the language translation and Gmail software. But before we begin, make sure to follow our Intellipaat channel to never miss an update about multiple digital technologies. First of all, we shall look into the agenda for today's session. We'll begin this session by understanding the term deep sequential modeling. After that, we'll discuss the difference between feed-forward and sequential modeling with the help of examples. And these differences will be mostly in the context of recurrent neural networks. Later, we'll dive deeper into the mathematical intuition behind recurrent neural network and the design criteria for RNN modeling. Finally, we will touch upon the concept of backpropagation through time in RNN and the programming intuition behind TensorFlow's simple RNN method. I hope I have made myself clear with the agenda.
So, without further ado, let's get started with our first topic, deep sequence modeling. Guys, before we dive into the theory, I would like to begin with a very simple intuitive example. Let's suppose we have a football here and our task is to predict where it is going to travel next. Without any prior information about the ball's movement or understanding of the dynamics of its motion, any guess on its next position is just going to be a guess or an idiotic speculation, right? Nothing more than that. But instead, in addition to the current location of the football, if I also present you its previous locations, then our problem becomes much easier, isn't it? And I think now all of us can agree that this ball is moving towards right direction. This particular illustration is the exact depiction of sequential modeling or sequential prediction. The problems of sequential modeling are abundantly available around us, which makes it an important aspect of machine learning. For example, the audio-like waveform that has been created by speech can be split up into the sequence of sound waves, right? The text can be split up into sequence of words. A word can be split into sequence of characters. All these individual characters or words can further be thought of as a time step in a sequence. Now, beyond these simple examples, there are many more cases in which the sequential processing can be useful. From the medical signals like EKGs to stock price graphs to genomics or genetic data and beyond. So now that we have gotten a sense of what sequential data looks like, let's think about the difference between the feed-forward and sequential data modeling. We'll be using two different examples to gather a strong sense of both these modeling techniques. The first example we are going to see is about feed-forward data modeling. You guys can consider feed-forward models as one-to-one mannered models. These deep learning models work best when there is no internal dependency between the data items. For instance, consider the imagery data. In imagery data, one image can be of sea and another image can be of a building. There is no dependency in these data values, right? And furthermore, these models come with fixed and static input which eventually gets trained over static and predefined output for predicting similar data samples when applied. Let me help you understand the feed-forward neural network with the help of an example. The person you guys can see on the screen is Rachel, and she is really organized person. Recently, she has decided that for the approaching monsoon season, she will wear the t-shirt when the day remains sunny. Otherwise, if it's rainy outside, she will prefer wearing a waterproof jacket. And in the context of deep learning, this problem can be modeled into a very simple neural network. If you are wondering what neural network is, then let me give you a brief overview about that. So, according to human biology, our brain does the processing of inputs gathered from sensory organs. The stimuli input is basically passed in the form of electrochemical events, scientifically known as neurotransmissions. The simple stimuli input is then processed by multiple neurons to produce an output or decision that our brain further signals us to do. The machine learning neural network is completely inspired from this neuroscience phenomena. In machine learning, once the numeric input and output is provided, we train the mathematical model which lets us predict, classify, or even cluster the similar type of data objects as soon as the proper learning is achieved. So this is completely a mathematical phenomenon, guys. So now coming back to our simple neural network modeling, you can say that the decision for Rachel will be completely dependent on weather conditions, right? So if we provide an input as a sunny weather, the resultant output that our model should return will be t-shirt. On the contrary, if the input is rainy weather, Rachel should wear a waterproof jacket. This syntactical data or logic is easy to process for human brain, but that's not the case with neural networks. Hence, have to convert these textual terms into numbers. In machine learning, we generally use one hot encoding for that purpose. But here, let me consider random vectors for all these parameters. We will be representing the wardrobe with some input vector having the same dimensions and the weather with some other input with different dimensions. The t-shirt vector will be 100, the jacket vector will be 010, the sweatshirt vector will be 001. Keep this sweatshirt value in mind too, since we'll be using this parameter in our next example, guys. Now, the weather parameter will have different dimensions than that of wardrobe. The sunny day will be represented with vector 10, whereas rainy day will be represented with vector 01. Let's do some math to understand how a neural network will transform the provided input into the output. So here we have the input, then we have weight matrix. Remember guys, weight matrix is something that you learn by training the model. It's not part of prerequisites such as input or output. However, for this example, I have computed the optimal weights to help you understand the working mechanism of a simple feed-forward neural network. After weight matrix, we have an output. So generally, we always have been provided with input and output for any problem. And we compute the weights parameter during the training period. Well, look at this formula, y is equal to wx plus bias. Here, y is nothing but the output, x is input, w is weight, and bias is the term that we add into the product of weight and input to round it up around value y. So intuitively, there is only one variable to compute, the weight, right? But since we have the optimal weight matrix here, let's analyze how the input is transforming to the output. As per the formula, the first step that will happen is the product of input and weight. So let's provide the vector sunny as an input and carry out this matrix multiplication. Now, this is how the matrix multiplication is done. The sunny matrix will be multiplied by each individual row of weight matrix, and after that, the resultant of each row will be mapped into a singular dimensional matrix or vector, which is nothing but the vector 100 that represents t-shirt. Now, let's also discover the result if we provide rainy vector as an input. Let's carry out the cross product of matrix weight and rain. The resultant matrix multiplication will look something like this, which will be nothing but 010 vector that represents the jacket. One thing if you have observed guys is the bias value for this whole model is 0. Basically this is because the data is quite small and there is no huge processing or computation going behind the model. So basically what model is doing is it is mapping the sunny weather into the t-shirt and rainy weather into the jacket. I hope this is quite simple enough. Now let's move to the next example involving sequential data. Let us say that Rachel has now decided to change the logic behind her daily wardrobe. She is planning to wear a t-shirt on the first day, jacket on the second, and sweatshirt on the third day. Let me elaborate this more. Let's say Rachel wears a t-shirt on Monday, which means she would wear the jacket on Tuesday. Next will be a sweatshirt on Wednesday. Later we will have t-shirt again on Thursday, jacket on Friday, sweatshirt on Saturday, and this will be continued so on. Here if you observe, the wardrobe is completely dependent on the previous day's wardrobe. There is a sense of dependability in our data, right? That is the reason why simple feed-forward neural network architecture won't work in this case. Let's figure out the architecture that could model this type of sequential data. Let's say a t-shirt is the output for day 1 and this output will be passed as an input to the model again. So when the t-shirt is entered as an input, it will get mapped into a jacket. And when a jacket is again fed to the network, it will get mapped into a sweatshirt. Next, when sweatshirt is fed to the network, it will get mapped into a t-shirt, and so on. So, if we collapse this into a basic timely representation, we could say that for day dt plus 1, dt, that is the previous day's output, will be fed into the network as an input. Also remember guys, in this example we don't have individual state input across every time step. But remember, that can also be provided as an input to the recurrent neural network. On that note, let's discover the mathematical intuition behind this algorithm. We have the input vectors and the pre-calculated weight matrix, using which we'll understand how the output is mapped. Let's pass a t-shirt vector as an input. The first thing that will happen is the cross product of weight and t-shirt matrix. The outcome of this matrix multiplication will be the resultant of the matrix, which is nothing but the vector representing jacket, right? If you guys want to visualize the model in form of neural network architecture, then here it is. The green dotted lines showed up in this network architecture are the ones with weight value 0, whereas the broad red lines represent the connection with weight value 1. Now let's say we pass a t-shirt as an input to this. Now these values will only travel across the connections that have weight values 1. This will make our output 0, 1, 0, which is the resultant vector of the jacket. Now, if I want to figure out the output for next time step, the jacket will be fed as an input and we'll get a sweatshirt as an output. If you collapse this illustration into a simplistic representation, you can say that the previous time state is acting as an input to the next time step in our model. This sort of backpropagation with respect to the individual time step in learning phase is the basic notion behind the incarnation of recurrent neural network. Let's list all the differences between feed-forward neural network and recurrent neural network that we have observed. The first significant difference that you guys should always keep in mind is the size of input and output is fixed, static in case of feed-forward neural network. We mentioned this at the beginning itself, right? Whereas if we talk about sequential modeling or recurrent neural network per se, the size of input dimension is by no means static. If you are working on a language translation model, the input-output format will be many to many. For the image captioning model, the input-output format will be one to many. And for the models like speech recognition, the input-output format will be many to one. The next key difference between both the modeling methods is the data they operate on. In case of feed-forward neural network, you'll have a special data which don't have internal dependencies between data points. For example, one image could be of a dog and another image could be of a cat for classification, right? There is no correlation or dependency between these two different images. Whereas the RNN or sequential modeling requires the dependency in data points. It uses temporal or sequential data that exist in format of videos, speech, text, and handwriting. The last difference we have is there is no need for memory feedback in case of feed-forward neural networks. They are simply processing in forward direction and not across different time steps. However, we can say the same for recurrent neural networks. These networks utilize long short-term memory or LSTM to backpropagate the overall loss. That's the discussion for some other day. But let us dive forward and understand the mathematical intuition behind the recurrent neural network. In the last section, we discussed one sequential real-life problem and modeled the solution for it using recurrence relationship. However, we did not have a new input at each particular time step. It was just about processing the previous time step as an input. So let me help you visualize how the actual recurrent neural network looks. Let's say at time t is equal to 0, we have input x0 and we feed it to the recurrent neural network, which after some time generates the output y-0. Next, suppose we do the same, take input x1 at time t is equal to 1 and isolately feed it to the recurrent neural network and we generate the output y-1. we keep doing the same for all the next steps in our data. Further, to emphasize here, all these models used are replicas of each other with different inputs at each different time steps, right? Thus, we all know that our output will be some sort of function of input x. But what we are missing here is the dependability of our output on its previous states. Since the data we have is sequential data, right? So we all have to do is find a way to communicate all the computations from previous time step as well as the input at the prior step to all future time steps. So what we propose to do here is introduce this internal memory or cell state, which we have denoted here as h of t. So this is basically going to be a memory that will be maintained by neurons and the network itself. What we are intending to achieve with recurrence relationship here is the notion of memory of what this sequence looks like. What I mean by that is the predicted output will now be function of both cell state and provided input at an instance. Now, if we collapse this structure down into a more generic form, it will look something like this. Okay. Let me formalize this a bit more, guys. The key idea here, as mentioned earlier, is that these RNNs maintain this internal state h of t, which is updated at each step as the sequence is processed. This is actually done with the help of recurrence relation that you guys can observe in the diagram alongside. Mathematically, this recurrence relationship can be represented as this formula here. The h of t in this formula is cell state at time t, which is the function of fw, meaning the function that can be parameterized by a set of weights w, which are what we actually trying to learn over the course of training such a network. The xt is again the input at time step t, whereas h of t minus 1 is nothing but the previous cell state. Let me give you guys a walkthrough towards output computation in RNN. We will start discovering the computation process from the bottom to top. Initially, we consider our input vector as xt and we are going to apply a function to update the hidden state. This function is a standard neural network operation commonly known as activation calculation, which we have formerly mentioned is a function of both previous cell state and current input apropos their respective weight matrices. We add both these products and then apply a non-linear activation function, which in this case is going to be hyperbolic tangent or tan h. The output that we will get out of this hidden state operation will be further propagated to compute an output by multiplying it with respective weight matrix, referred as W from H to Y. I hope this sort of gives you the mathematics behind how RNN can actually update its hidden state and also how it can produce a predictive output. So far, we have seen RNNs being depicted as having these internal loops that feedback on themselves, and we have also seen how we can represent this loop as being unrolled across time, where we can start from first timestamp and continue to unroll the network across time up until time t. And within this diagram, we can also make explicit the weight matrices starting from the weight matrix that defines how the input at each time steps are being transformed in the hidden state computation, as well as the weight matrices that define the relationship between prior hidden state and current hidden state. And finally, the weight matrix that transforms the hidden state to the output at a particular time step. Again, to re-emphasize in all these cases, for all these weight matrices, we are going to reuse the same weight matrices at every time step in our sequence. With the forward pass through the network, we are going to generate outputs at each of these individual timestamps represented as y-0, y-1 and y-n. And by subtracting the predicted output from the actual output, we could formulate the loss for each time step across the data. And then, summing up all these losses together, we could determine the total loss. This whole process till computing the overall loss is considered as a forward pass in deep learning. Moving forward, to build more context on why recurrent neural networks are so powerful, I would like to consider a concrete set of sequence modeling or architecture criteria. The first point I would like to put across is that we need to ensure that the model we are creating should be equipped to handle variable length sequences, because not all the sentences or sequences are going to have same length, right? Thus, we need to have the ability to handle this varying variability. We also need to have this critical property of being able to track long-term dependencies in data and to have a notion of memory. Alongside that, we also need the ability to have this sense of order. And we could achieve both these 2 and 3 by using the weight sharing mechanism. The recurrent neural network do indeed meet all these design criteria. How do they achieve this? Is another point of conversation that we could address in some other video. Well, for now, let's arrive back at our next point, that is backpropagation through time in recurrent neural networks. First of all, we shall take a step backward and understand how backpropagation in feed-forward neural network occurs. At the beginning, we take a set of inputs and make a forward pass through the network, going from the input to output. And then, to train the model, we backpropagate net gradients back through the network. We actually do take the derivative of these losses with respect to each weight parameter in our network and then adjust parameters precisely to minimize the loss. For RNNs, as we walked through earlier, our forward pass through the network consists of going forward across time and updating the cell state based on the input as well as the previous state. After that, we compute the individual output and loss for each time step, and summing those loss values further, we determine the overall final loss. In RNN, instead of backpropagating errors through a single feed-forward network at a single time step, we backpropagate the complete error for our model across each time step, all the way from overall loss to the beginning of the sequence. This is the reason why it's called backpropagation through time, because as you can see, all of the errors are going to be flowing back in time from the most recent time step to the very beginning of the sequence. Now, if we expand this out and take a closer look at how gradients can actually flow across the chain, we can see that between each time step, we have to perform this matrix multiplication that involves the weight matrix WH of H. And so, computing the gradient with respect to the initial cell state H of 0 is going to involve many factors of this weight matrix and also the repeated computation of gradients with respect to the weight matrices. This can be problematic for a couple of reasons. The first being that if we have many values in a series of matrix multiplication where the gradient values are greater than 1 or the weight values are greater than 1, we can run into a problem called exploding gradient, where our gradients are going to become extremely large and we cannot really optimize them. The solution to this problem is to do what is called as gradient clipping. It is the process of effectively scaling down the values of particularly large gradients to try and mitigate this risk of exploding gradients. We can also have the opposite problem where now our weight values or our gradients are very small, and this could lead to what we call as vanishing gradient problem. In this problem, the gradients become increasingly smaller and smaller such that we can no longer effectively train the network. There are 3 ways in which we can address this vanishing gradient problem. We will discuss them briefly one by one. But before discussing that, you would need some intuition about why vanishing gradient could be a problem. Let's imagine that you keep multiplying these small numbers, a number between 0 and 1 by another small number between 0 and 1. The resultant for sure is going to shrink and eventually it will vanish. When this occurs, it is going to be harder to carry out gradient and propagate errors from our loss function back into the distant past, since we have this problem of gradient becoming smaller and smaller. Ultimately, what this will lead to is we are going to end up biasing the weights and parameters of the network to capture shorter term dependencies in the data rather than looking out for longer term dependencies. And this is exactly going to hamper the design criteria that we discussed previously, right? Now, how we can actually get around this? Well, the first trick we are going to consider is pretty simple. We can smartly select the activation function. Specifically, what is commonly done is to use the ReLU activation function, because the derivative of this function is greater than 1 for all instances where the x is greater than 0. And this helps the gradient with respect to the loss function to actually shrink when values of input are greater than 0. Another method would be smartly initializing the weight parameters. We can specifically initialize weight to the identity matrix to be able to prevent weights from shrinking to zero completely and very rapidly during backpropagation. Our final solution and the most effective and robust solution is to use more complex recurrent units that can more effectively track long-term dependencies in the data. By intuitively, you can think of it as controlling what information is passed through and what information is actually used to update the cell state. Specifically, deep learning employs gated cells such as LSTM or long short-term memory or GRE to attain that. But this is yet complex concept to discuss on some other day. For now, just remember that these are the ways to avoid vanishing gradient problem. Let's move to the last topic on our agenda, that is understanding the programming intuition behind the TensorFlow's simple RNN module. We are going to define the RNN using a layer here, so we can build it up from Kera's layer class. We can also initialize the weight matrices and hidden state of the RNN to all the zeros. Our next step is going to be defining the call function, and this function is really important because it describes exactly how we are going to make a forward pass. Our first step here is going to be updating the hidden state according to the same equation that we saw in hidden state. The following step will be calculating the final output and returning it alongside the current state that we have computed. All of this algorithm is embedded behind one simple TensorFlow syntax that you will be using ahead to develop recurrent neural networks. However, this doesn't cover the backward pass, or neither does it solve the problem of vanishing gradients. But that is not the concern for now, because we will have a detailed tutorial on that coming up next. I hope the basic intuition of RNN covered in this tutorial is clear to all of you guys out there. Thank you so much for watching the video, and do subscribe to our Intellipaat channel to receive more such extensive tutorials on different digital technologies.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.